Hey everyone, this is our first video on Chapter 3 of our Elementary Statistics book. Chapter 3 is all about describing, exploring, and comparing data. Okay, so we're going to be starting, in this video we're going to be focusing on section 3.1. This is actually part 1 of 2 videos that I'm going to make covering 3.1. So 3.1 is all about measures of center. And here we're going to be doing just part 1, calling this part 1, because in this video we're going to learn how to do the mean, the median, the mode, and the mid-range. So 4 words that all start with M. And those are some of the most common measures of center. And of course the word center already gives away what we're trying to calculate. We have a bunch of data values and we want to have some number that describes roughly where the middle of the graph is. Okay. And then I will also make another video which is going to be measures of center part 2, and in the second video, the one that comes after this one, I will be talking about weighted means, which in the real world people are used to calling weighted averages. Okay. All right, but this is just part 1. Okay, so measures of center. So there are a lot of slides here. That's why I'm going to break it up into 2 videos. But in this section, we'll be learning about a total of 5 measures of center. We're going to learn the first 4 of them, so mean, median, mode, and mid-range in this video. And then in the next video that I make, I will be doing the weighted mean. Okay. Our objective here is not only to find the value of each measure of center, but also to interpret those values. So what do those values tell us about the behavior of our data, and what kind of things can we extrapolate from that information? All right. Okay, so what is a measure of center? Well, obviously the word center kind of gives it away. The middle. Okay, so a measure of center is a value at the center or middle of a data set. But that's kind of a very loose way of saying it. Because who's to say where the middle really is? I mean, looking at a graph, if we see a graph like a histogram, we might think that the middle would be where the maximum is, because that's the highest point. But if you actually calculate the measure of center, it might not necessarily be at the highest point. So it all depends on how the data is distributed, so what the shape of the graph is. Okay, so we're going to start with the most important measure of center that most people hopefully have seen from the real world. Now in statistics we call it the mean or arithmetic mean, but in the real world most people call this the average. Okay, so the mean or arithmetic mean of a set of data is the measure of center found by adding all of the data values and dividing the total by the number of data values. Okay, so that's just the same as the average that most people have seen, at least in school and probably in the real world. So the way you find the average of a set of numbers is you add up all the numbers and then you divide by the number of numbers. But in statistics, we're not supposed to call it an average, as you'll see on this next slide. So caution, even though in the real world we might like to call the mean an average, when we're doing science or statistics, you're not technically supposed to use the word average. I will throw it in from time to time in the videos. I'll call something the average. But for your homework, quizzes, and exam, our book kind of makes a big deal about this, to not call it the average. So the word average is often used for the mean, but is sometimes used for other measures of center, and for that reason, that's why the term average is not used by statisticians. The term average is not used by the statistics community or professional journals. Science journals don't usually use the term average, they just call it the mean. And the reason for that is just the word average is kind of like the word center. So it's a little bit ambiguous. So average doesn't have to necessarily be the mean. Okay, but the mean should be very straightforward to calculate, especially with a calculator. Let me skip ahead to this slide. So here's the formula for the mean. So this part might look a little confusing, but all this means is the sum of all data values, which means you add up all the data values, and then you divide by the number of data values. So the way we read this is sum of x, where x is each data value, divided by n, where n is the number of data values. And it actually turns out that when you're calculating the mean, you're always going to use this formula. And it doesn't matter whether you're calculating a sample mean. So if it's a sample mean, we'll call it x bar. So it looks like x with a horizontal line above it. That's called x bar. This right here, that's for a sample. That's the mean for a sample. And then if the data are for the entire population, if you somehow have gathered all the data values for your entire population, then the mean would be denoted by this Greek letter here, which is called the lowercase Greek letter mu. Some people say mu, other people say mu. I've heard both. But it kind of looks like a U, and then also it looks a little bit like a Y. Some people, the way they write it, it also looks like an M, which kind of makes sense with the name mu. It starts with M. But anyway, it turns out that regardless of whether you're taking the sample mean, x bar, or the population mean, mu, you're still going to use the same formula. So it's going to be the sum of all the data values divided by the number of data values. So this notation here is what we're going to talk about. So this symbol here is called the summation symbol, which just means that you add up all the data values. So people read this as sum. It's technically a Greek letter sigma, but people don't usually say sigma. It's called sigma notation, but people, when they see this symbol, instead of saying sigma, they just say sum, which just means you add up all the data values. X is the variable usually used to represent the individual data values. Okay? N represents the number of data values in a sample. So that's lowercase n. Uppercase N, which we don't see as much, uppercase N represents the number of data values in a population. Okay, but like I said, regardless of whether you have a sample or all the values for the population, you're still just going to be doing the same thing. So once you get used to the notation, notice that these two formulas here really are saying the same thing. So this one is x bar, that's the sample mean. And for that one, you add up all the sample values. That's what sum of x means. Sum of all x values. So you add up all the sample values, and then you divide by n. Lowercase n is the number of sample values. Okay, that's x bar. That's the sample mean. Mu is the population mean. And it's the same exact process. So mu equals sum of x. Here, x is referring to all the data values in the population. And then capital N actually represents the size of the entire population. Okay. But once you get used to this notation, which you do need to get used to, Actually calculating these is very straightforward. It's mostly just getting used to all the new letters and the notation. But the rest of it should be pretty straightforward. Okay, so let's jump into an example. We'll talk a little bit more about why the mean is useful, but for now, let's just jump into an example. So, example on the mean. One of the data sets from our book is for Disney World wait times. And that includes the wait times for 6 popular rides in Disney World. Okay? And they want us to find the mean of the first 11 wait times for Space Mountain at 10 a.m. So these are the wait times gathered by the author of our book from the real world, and we just want to find the mean. So here, this is obviously going to be a sample because this doesn't include all of the wait times at Disney World for all of the rides. That would be the population. So we're not calculating a population mean. We're calculating the sample mean, which is going to be, the formula is x bar. So it looks like x with a horizontal line above it. And this equals, in the numerator, we have sum of x. So the sum of all the data values divided by lowercase n in the denominator. But weird notation aside, it's not that weird once you get used to it. That just means on the top, we add up all the numbers. So in the numerator, we're going to be doing 50. Actually, let me give myself a little bit more room here. So I'm going to start over here so I actually have enough room. So x bar equals sum of x. That's our numerator. And that one is going to be adding up all these values. So 50 plus 25 plus 75 plus 35 plus 50 plus etc. All of these numbers all the way plus 20. I got lazy. I didn't want to keep writing them. Okay, so I'm just adding them up. And notice when I'm calculating the mean, which most people in the real world would call the average. But when I'm calculating the mean, I don't have to put these numbers in order. So these data values don't need to be put in order. But just remember, your data values are the same as x. Okay? So here x, the letter x is actually represented by all of these data values. So sum of x is what we just did here, where we add up all those data values in the numerator. And then the denominator, we divide by n. So what's n going to be here? Well, you can either just read, they told us there were 11 wait times, so n is going to be 11, or you can just count. If you have all your data values like we do here, you can actually just count how many data values you have, and that'll be n. Okay, so like here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 data values. So that means n equals 11. N equals 11 data values. Okay, so that means we're going to add up all these numbers and we're going to divide by 11. Okay, and then most people would want to use a calculator for this. So let me grab my calculator real quick. So if you want to type all these all at once into your calculator, you probably are going to need to put parentheses around the numerator, so around the top. If you want to type all this in all at once on your calculator, you would probably need to do that. Or the other thing you could do is you can just add up all these numbers on your calculator and then see what that is and then divide. So either way is fine. So 50 plus 25 plus 75 plus 35 plus 50 plus 25 plus 30 plus 50 plus 45 plus 25 plus 20. So when you type them into your calculator, it's always good to just make sure you typed in the right numbers. So right now, I'm just going to look at the numbers that I typed in, which is a good habit, especially if you're taking an exam in my class or another class. You definitely want to check your work. But it does look like I typed in all the numbers correctly. So when I add up all those numbers, that will give me 430 in the numerator. So we have 430 over 11. And that's 430 divided by 11 on my calculator, which is 39.09. 39.09. Okay, and this is assuming I typed all that in correctly. Obviously, it's not too difficult, but if you miss a single number, it can throw off your numbers. So let's see what they got on the slides to see if they got the same thing. Okay, so on the slides, this is straight out of our book. They did this same example. As you can see, they have all the numbers written out. Sum of x is going to be the same thing we wrote, and then n is 11. And they also got 430 divided by 11, but then they rounded it to 1 decimal place. So why did they round it to 1 decimal place? Well, there's actually what's called a round-off rule way later in these slides that I wanted to just talk about while we're thinking about it. So in this slide, we can see that the round-off rule for measures of center, remember what we're learning about here are measures of center. For the mean, median, and mid-range, you're supposed to carry 1 more decimal place than is present in the original set of values. Okay, so 1 more decimal place than is present in the original set of values. So if we go back to the example that we were just doing, we're going to notice that they rounded to, let's see, let me get back to it here. They rounded to 1 decimal place. So why did they do that? Well, if we look at the original data values on the previous slide, look at this one, we can see that the original data values had, all of them had 2 digits, right? So 2 digits. So that means when we're writing out the mean, we're supposed to round to 1 more decimal place than these original data values. Well, these original data values, if you will, don't have a decimal place. So that's like they're rounded to 0 decimal places. Decimal's right there, to the right of those numbers. So we just do 1 more than 0 decimal places, which is 1 decimal place. So 39.09, we're looking at the 0. The next digit is 5 or higher, so we round up. So that's how we get 39.1. Okay? So that's how they got 39.1. And if you're doing your homework, quizzes or exams, on a lot of the problems, if you look directly below where you type in your answer, it will tell you how many decimal places to round to. Excuse me. Okay, so we've learned about the mean. It's a very very easy thing to calculate. Excuse me. Okay. So that is the mean. That is the first measure of center and probably the most important measure of center. So before we go on to the other ones, I do want to talk about the strengths and weaknesses of the mean. So, on this slide, important properties of the mean. Sample means drawn. Excuse me. Sample means drawn from the same population tend to vary less than other measures of center. That's an interesting fact. Not too useful to us, but it's a good thing to know. Next interesting fact is the mean of a data set uses every data value. So you will notice that the calculation that we just did, we used every single data value. So we used all of these numbers. The fact that we use every data value is probably a good thing. Most people think that's a good thing. The reason that's a good thing is then we actually have, we're measuring something that takes into account all the data values. That's important. So really, these first two important facts are positive things to say about the mean. This third fact is kind of a negative thing. So a disadvantage of the mean is that just one extreme value, which is also known as an outlier, can change the value of the mean substantially. Okay, so we're going to learn about the following definition on the next slide, which says that the mean is not resistant. So we say the mean is not resistant. What does resistant mean? Resistant, a statistic is resistant if the presence of extreme values or outliers does not cause it to change very much. So if you look at the mean, the reason it's not resistant is because it includes every data value. So like if we go back to this example, if I include one more data value that's an outlier, remember an outlier is a number that is far away from the other numbers. So for example, if we included one more wait time that was like, say, 130 minutes, let's say we have one more data value of 130 minutes. What do you think that's going to do to the mean? Well, because the mean includes all the data values, it's going to drastically increase the mean. So the mean is going to go up a lot. So that's why we say the mean isn't a resistant measure of center, because it doesn't resist data values that are unusually high or unusually low. Same thing is if instead of 130, someone had a wait time of, say, 5 minutes, that would be another example of an outlier. What do you think that would do to the average, or the mean is what we're supposed to call it? Well, because it's so much lower than the other numbers, when you add up all these numbers, it's going to lower the average or the mean by a lot. So just remember, numbers like 5 or 130 that don't really belong with these other numbers that are far away are called outliers. And because the mean includes all the data values in its calculation, it's not resistant to outliers, which is just something to keep in mind. Now, in our class, we're not going to be doing trimmed means. I know some instructors do what's called a trimmed mean. So like if you think about it, if you have, say, the two outliers that we were talking about. Let's say you have a 5 here, and then I forget what I wrote, 130 over here. What some people do is they make a trimmed mean in which they take out outliers, and then they just calculate the mean without the outliers. So again, we're not going to be doing a trimmed mean, but I'm just going to mention that the way a trimmed mean works essentially would be you would take away the 5 and you would take away the 130, which are outliers. And then you would just calculate the mean of these numbers in the middle. And obviously that's a good idea if you don't want to include extreme values that are going to, drastically raise or lower the mean. Okay, but we're not doing trimmed means in this class, so I'm just mentioning them. All right, so we've talked a lot about the mean. I know it's a bit boring because most people know how to calculate the average already, so it's really just a different name and this weird notation that most of you probably haven't seen before, unless you've taken statistics before. But it's good to understand all this stuff, even if it's a bit boring. All right, so we've learned about the mean in great detail. Next topic is another measure of center. Probably the second most popular measure of center besides the mean or the average, as people call it, is the median. So the median of a data set is the measure of center that is the middle value when the original data values are arranged in order of increasing or decreasing magnitude. Okay. Technically, it doesn't matter whether you put them in decreasing or increasing order, but most people just put them in increasing order. That's pretty standard because it's usually easier to just write them, smallest number first, cross it out, next smallest number, and so forth. So this is a lot of fun to calculate because all you have to do is put the numbers in order and then either count in from the ends or just look at the numbers and figure out whether there are 2 middle numbers or 1 middle number. So here it says middle value, but if you have an even number of data values, then you may have 2 middle values, in which case you have to add up the 2 middle values and divide by 2. But it's still not too bad. It's pretty straightforward. So I'll talk more about why the median is useful, but I do want to jump into an example. But to calculate the median, and it's sometimes denoted with X with a tilde on top of it, or some other books call it capital M, or they'll just write MED to represent median. All those things mean the same thing. To find the median, first you sort the values, arrange them in order, and then you follow one of these two procedures. Like I said, once they're in order, you can almost just look for the middle by just counting in from the ends. Or alternately, you can read what they have in the book. So in our book, they say if there are an odd number of data values, the median is the number located in the exact middle of our sorted list. However, if the number of data values is even, the median is found by computing the mean of the exact 2 middle numbers. So that just means you add up the 2 middle numbers if they're an even number of data values and you divide by 2, which is not too bad. Okay, so I'm going to do an example of each type of median. So we're going to use the same data values that we did on the last example when we calculated the mean. So here we want to find the median of the first 11 wait times for Space Mountain. Okay. So with the median, you do have to put the numbers in order. So your first step is to just arrange them in order. And again, most people put them in increasing order. That's just pretty standard. So to do that, the most mindless and easy way to put the numbers in order is to just look through the numbers and first identify which one is smallest. Okay, and then whatever the smallest number is that you see in all the data values, you cross it out and then you write it down. Okay, actually let me write it down here so I have lots of room. So 20 is the smallest data value that I see, and there's only one 20, so I cross it out, and that's my first data value. And then I just continue this process over and over again until I've crossed out all the data values. So now I look through the ones that are left that I didn't cross out, and I look for the smallest number again. So here I see 25, 25, 25. So I need to count how many of them there are if they repeat like that. So here there's 1, 2, 3 25s. So now I'm going to write 25, 25, and 25. Okay? And then we just continue this process. So now with the numbers that I haven't crossed out, what's the smallest number? I see a 35 here. A 30 is definitely the smallest. And I only see one 30, so I'm going to cross out that 30 and write it here. I probably shouldn't write so much space in between these numbers. I'm going to run out of room. So we've got 20, we've got 3 25s, and then we've got 130 that we just did. Okay, continuing this process, for the numbers that are not crossed out, we can see that the next smallest number is 35. Okay, so we write down 35. There's only one of those. And then after 35, the next smallest number would be 45. So we cross out that one. And then the next number would be 50, but we have more than one of those. So we have to count how many 50s there are. So there's 1, 2, 3 50s. So I'm going to write all 3 50s here. So 50, 50, 50. And of course, I've already crossed out all the other numbers, so the only number remaining is 75. So I write that last. So over here, I'll write 75. Okay. And it's a good thing I wrote the numbers closer together because I barely had enough room to write all that. So if you want to do it the way they do in the book, you would count the number of data values. So here there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 data values. And then if there are an odd number of data values, the way you calculate the median is, let me go to this real quick. With an odd number of data values, the median is the number located in the exact middle of the sorted list. That's how they do it in the book. So here, because 11 is an odd number, then we just look for the middle here, which you pretty much, the best way to find the middle would be my way of finding the middle, which is, especially when you don't have that many data values, you could just start on the ends and then just count in by 1 until you reach the middle. So here I'm starting at the ends. 1, 2, 3, 4, and then boom. We can see that I've arrived at the middle, and there's only one middle value. So here, because there's only one middle value, that's the value of the median. So what do we get? This is x tilde, or the median. So x tilde equals 35. So now I wanted to point out that even though the book says on the previous slide, the book says that you need to break it down based on whether there are an odd number of data values or an even number of data values. I want to point out that in most cases, that's not really necessary. You can just do what I did, which is you start at the ends, and then you work your way inward one by one until you're at the middle. And then when you're at the middle, you will see that there's either one number in the middle, like in this case, or there will be 2 numbers in the middle. And if there are 2 middle numbers, that means you have to average them or add them up and divide by 2, technically taking the mean of the 2 middle values. Okay, So that's median with an odd number of data values. But I think you're going to find that once you put them in order, my method of counting inward from the edges is easier than having to worry about whether they're an odd number of data values or an even number of data values. Okay. All right. So I wanted to do another example of the median where we do for an even number of data values. So we're going to have all these same numbers, but they're going to add in one more number. So instead of having 11 data values, we're going to have 12. By the way, on the slides here, they say the same stuff that I was just talking about. It's just this is the way they do it in the book. So for the odd number of data values, they circled the middle data value, and that's the median. The only thing to be careful about here is I wrote that the median was x tilde was 35.0. Well, sorry, I said x tilde was 35, but what I meant to say was that x tilde should be 35.0. Now, why should it be 35.0? Just remember that we're supposed to have one more decimal place than what we started with. So these data values were at 0 decimal places, so I was supposed to write 35.0 for the median, not 35. But it should be very clear when you're doing your homework what you're supposed to round to, because on my math lab, below each place where you type in your answer, it will say what to round to, directly below where you type in your answer. So it's not too difficult. Okay, so yeah, median with an odd number of data values. In this next example, we're going to use almost the same data values. They've just added in one more. So you notice here, they've actually just added in one more 50. So on the one that we did previously, there were 3 50s. But now with this one, they've added in one data value, which is another 50. All right, so without having to write it all on the board again, which takes up a lot of time, let's just go to this next slide. So they have arranged these data values in increasing order or ascending order. Ascending just means increasing. So then you can either do it the way they said, which is because they're an even number of data values, the median is found by computing the mean of the two data values in the middle, or alternately, you can just do my method, which is to start on the ends and then just count inward. 1, 2, 3, 4, 5. So here we can see that these are the two middle values. So, is that right? 1, 2, 3, 4, 5. Oh, okay. I don't know what I did there. I ended up here. That was not good. So 35 and 45. Sorry, I think I might be getting sick. You heard my coughing. But anyway, here we can see that the two middle values, either by counting inward or just looking at them, are going to be 35 and 45. And because there are two middle values, we just need to average them. So we do 35 plus 45 all over 2. So on your calculator, 35 plus 45 is going to give you 80. And then 80 divided by 2 is 40. But remember, you want to have one more decimal place than the original data values. So because these were, the original data values had 0 decimal places, now we want to have 1 decimal place. Okay. Cool. Okay, so that is the median. Now, why do we care about the median? What's so great about it? Well, it has some qualities that the mean doesn't, which are useful. So let's talk about usefulness, important properties of the median. So probably the most useful thing about the median that's actually better than the mean is that the median does not change by large amounts when we include just a few extreme values. Okay, so we say the median is a resistant measure of center. And resistant just means it resists outliers. So if you put in a very large value or a very small value that's an outlier, that's far away from the other values, it's not really going to affect the median a whole lot in most cases. One thing that's kind of negative about it, though, is that the median does not directly use every data value. For example, if the largest value is changed to a much larger value, the median does not change. Well, that's sort of the same thing that we set up here. So if you look at this one that we just did, if you think about it, I could add an outlier at the beginning and an outlier at the end. So I could put a very small value of 5 here, which is an outlier. And then I could put a large value over here, like 180 minutes. Now, if we were calculating the mean, these outliers could really change our numbers, or change our mean by quite a bit. But if we're doing the median, we would find that, for example, if I put this outlier here and that outlier there, we would still count inward, and we would still end up with exactly the same median. So here, I put in 2 outliers at the beginning and the end, and I still got 35 plus 45 over 2, which is still 40. So as you can see, that there's a big difference between what happens with the median. It's resistant to these outliers versus with the mean. As you can imagine, if you put 180 and you add that up to all these other values and then you divide by the number of values, that 180 is going to increase the mean by a lot. So the mean is not resistant and the median is resistant. So most people think that that's a really good thing about the median, is that it is resistant. Okay, so I think we've pretty well gone through everything for the median now. Hopefully that's helpful. Okay, so far we've done the mean, the median. Okay, next one is the mode. All right, so mode is another measure of center. So the mode of a data set is the value or values that occur or occurs with the greatest frequency. So the way I like to think of this, you may or may not like the way I think of it, but this is the way I remember it, is the mode is essentially the most popular number or numbers. Okay, so most popular number, because sometimes you could have one mode, or numbers. You can actually have more than one mode. So even though it's a measure of center, it turns out that you can have more than one mode, or you can have no mode, or you can have exactly one mode. So there are a lot of different cases. So what do I mean by the most popular numbers? I just mean the numbers that occur more than the others. So if there are clearly some numbers that are occurring more than the others, and they both occur the same amount, then you would have 2 modes. Okay, so if there are 2 numbers that occur that are most popular, and for example, they both occur 3 times, then they both win the popularity contest, and so then you would have 2 modes. But we'll see all the different cases. Okay, so let's jump into an example or 2, so you can see what I mean. Example on the mode, find the mode of the same data value, so 11 wait times. Okay, these are, I want to say these are different numbers than when we worked on the last example, but these are still taken from the book. They're just, some different wait times than the ones that we looked at. Okay, so how do you find the mode? To make it easy, I do recommend that you do sort the data values in increasing order or ascending order. So you would just go through the same process that we did before. I'm not going to go through it all over again. But you would find the smallest number, which here is 20. And there's only one of those. So you cross that out, and then you get the first number, 20. And then the next smallest number would be 30. You see two of those. Cross those out, and you write the two 30s. And then you would find three 35s and so forth. But we already did that in an earlier example, so I'm not going to go through all that again. So these are already sorted down here, and here with these numbers arranged in increasing order, it's very easy to see what the most popular numbers are. So there are two 30s, there are three 35s, so 35 is more popular than 30. There are two 50s, so 35 is also more popular than 50. And then all the other numbers, 20, 45, 75, and 95, each of the other numbers only occur once. So clearly the most popular number here in this list would be the 35, because there are three of them. There are three of them, and no other numbers occur three times. So we say that this only has one mode, which is 35. So 35 wins the popularity contest, most popular number. So the mode is 35. Because it is the value occurring most often, it occurs three times. Okay, and that's an example of having one mode, because there was only one number that beat all the other numbers. It won the popularity contest. Okay, so let's see examples of, we've seen one mode. On the next slide, let's see some other mode examples. So what would it look like to have two modes? Well, here's a quick example here. So for the numbers 30, 30, 50, 50, and 75, if we just look at those numbers, we're going to notice that there are two 30s, there are two 50s. Use a different symbol for the 50s just so that we can count them. And then there's only one 75. So what are the most popular numbers? What numbers occur more than the others? Well, we have two 30s and we also have two 50s. So 30 and 50 are sort of have like a tie for the popularity contest because they both occur twice. And then 75 is definitely not going to be a mode because it only occurs once. So that means because 30 and 50 are the most popular numbers, but they both occur the same amount, they both occur twice, it's a tie. It's a tie for the popularity contest, so it has two modes, 30 minutes and 50 minutes. So hopefully that makes sense. Most people don't find this stuff too challenging. Okay, no mode. So what does no mode, what is that going to look like? Well, here's an example of that. So 20, 30, 35, 50, and 75. Well, we have 120, we have 130, 135, 150, and 175. Did any of these numbers occur more than the others? The answer is no. So if they all occur the same amount, instead of saying that everybody wins the popularity contest, what we do is we say nobody wins the popularity contest. So there's no contest because if each number occurs the same amount, no number stands out from the others. So we say there's no mode. And just real quick, just one more example. I wanted to show you one more example. Let's take a look at numbers. So let's take a look at 1, 1, comma 3, comma 3, and then 5, comma 5. So take a look at these numbers. Do you think this has 1, 2, 3 modes, or does this have no mode? Think about that for a second. You can pause the video if you need to. And then actually the answer is this would have also no mode. So the reason that this data set here would have no mode is 1 occurs twice, 3 occurs twice, and 5 occurs twice. So all the numbers occur the same amount with the same frequency. So no number, once again, wins a popularity contest. So for this example, we would say there's also no mode. Okay, so that's another example of no mode. So they don't have to all occur once. They just have to all occur the same number of times to say that there's no mode. All right, so then what is useful about the mode? Why do we care about the mode? Well, let's take a look at some of the descriptions of why the mode is useful and things to watch out for from our book. So going back to this slide here, that's what I wanted to talk about. Important properties of the mode. The mode can be found with qualitative data. This is the only measure of center that we're learning about, in this video at least, that can be found with qualitative data. Now remember that qualitative data is actually the same as categorical data. So categories or names rather than numbers. Okay, so how can it be done with qualitative data? Well, just imagine if instead of having, in all the examples we've been doing in this video, we saw numbers. But if instead of that you have categories, so for example, you might ask people what their favorite type of ice cream is. And then let's say you have 7 people in the study, and let's say that they only get 3 choices, just to make it easy to gather. So let's say the 3 choices so favorite flavor. Let's ask, if we ask 7 people what their favorite flavor of ice cream is, and like I said, just for the sake of making it easy to give you an example, let's say that the choices are vanilla, chocolate, or other. Maybe we had, let's say we had 2 people who said vanilla, and then maybe we had, say, 4 people who said chocolate. I'll just write C, because I'm going to run out of room. So chocolate, 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 chocolate. And then maybe 1 more person said other. Like maybe that person said mint chocolate chip. Anyway, the whole point of this example isn't to worry about ice cream, but more to point out that vanilla, chocolate, and other is qualitative data or categorical data. Categories are names or labels. And you can actually find the mode here because you just look at the frequency of each category. So here we can see that there are 2 vanillas. There are 1, 2, 3, 4 chocolates. And then there is 1 other. So you can actually find the mode here as a measure of center. Even though we don't have numbers, we actually have categories here. We could all see that the most popular ice cream flavor in this invented example would be chocolate, because chocolate occurs 4 times, vanilla only occurs twice, and other only occurs once. So here we would say the mode for this data set is chocolate. Okay, but that's just an example of how you can find the mode with qualitative or categorical data. All right, a data set can have no mode or one mode or multiple modes. No mode, one mode, or multiple modes. That's an important property. We've already seen examples of that. But that's useful. Like none of the other measures of center with the mean and the median, there's only one mean and then there's only one median. But a cool thing about the mode is that you can have more than one mode or you can have no mode. So that's an interesting and important property of the mode. Okay. Just real quick, I want to go through this slide. A data set, as we said, can have one mode, more than one mode, or no mode. This is just some interesting terminology to know. When two data values occur with the same greatest frequency, each one is a mode, and the data set is said to be bimodal. And the prefix bi, like in bicycle, bicycle has 2 wheels. Bimodal means it has 2 modes. Okay, next one. When more than 2 data values occur with the same greatest frequency. We haven't seen this, but you can actually have 3 modes, 4 modes, 5 modes. You can have a lot of modes. Each one is a mode, and the data set is said to be multimodal. So for example, trimodal would be an example of multimodal. So trimodal would mean that it has 3 modes. Okay, when no data value is repeated, we say that there is no mode. We already knew that though. Okay, so that's just good to know that there are names for these different situations that you encounter with data. Okay, so we've gotten through the mode. Hopefully you're still hanging in there. I know this video is going to be pretty darn long. But, you know, hopefully you aren't in too bad of a mode right now. And hopefully you don't find me to be a mean teacher either. Mean teacher. Okay, let's see what we did there. Okay, so mid-range. All right, so this is the last measure of center that we're going to be learning about on this video. Honestly, the mid-range is less useful than the other measures of center that we've learned about, because the mid-range of a data set is just the value halfway between the maximum and the minimum. So you add the maximum data value to the minimum data value, and you divide by 2, which is kind of the same process we did. Remember when we were calculating class midpoints in 2.1 for frequency tables? We would take the lower class limit and the upper class limit, so the minimum and the maximum for that class. We would add those up and divide by 2 to get the class midpoint. Mid-range is just another type of midpoint. It's called the mid-range because it's halfway between the lowest data value and the highest data value. Obviously, the problem with this right off the bat that you should be noticing is that it only takes into account the largest data value and the smallest data value. It doesn't consider any of the other data values. So it's not as useful as the mean, the median, and the mode. But we're still going to learn about it because you need it for your homework, quiz, and exam. It's very easy to calculate. That's a good thing about it. Because the mid-range uses only the maximum and minimum values, this is the slide I meant to be on. The mid-range is very easy to compute. That's a good thing about it. Another good thing about it is the mid-range helps reinforce the very important point that there are several different ways to define the center of a data set. Right? Now we have 4 different ways of talking about what could be the center of our data set. Another reason we're talking about it, other than the fact that you have to do it on your homework, is the value of the mid-range is also sometimes used incorrectly for the median by people who are not doing good statistics. So confusion can be reduced by us learning about it. That's what they say in the book. Okay, but obviously the elephant in the room is going to be that the mid-range is not resistant at all. So if you have the minimum value, that's the smallest data value, and the maximum value, that's the largest data value, if one or both of those are outliers, then it can hugely affect the mid-range because you're only looking at the minimum and the maximum. So for the mid-range to even be useful, you really shouldn't have any outliers. Because if you have a really high maximum or a really low minimum that's an outlier away from all the other data values, the mid-range is going to move up a lot or move down a lot. And it's just, it's not really including anything besides the maximum and the minimum. So it's not used as much because it's not resistant. All right, so let's just go ahead and find the mid-range here. It's supposed to say find the mid-range on this slide. I need to fix that. Hopefully I fix that before I post it. Okay. Anyway, this is supposed to say find the mid-range of the first 11 wait times. That's bothering me so much. I'm going to fix it during the video. Find the mid-range of the first 11 wait times. There we go. Okay, so all you do is use the formula. Mid-range equals maximum plus minimum divided by 2. So here, for these data values, we can see that the maximum is the largest data value, which is here going to be 75. That's our max. By the way, my cat is named Max. I bet you didn't know that. Okay, so my cat is named Max. Good to know. And then the minimum is going to be 20. And that's the minimum. Can anyone guess what my first cat was named? My current cat is named Max. My last cat was named Minnie. Yes, I'm really that much of a nerd. Okay, so maximum plus minimum divided by 2 is going to be 75 plus 20, which is 95 divided by 2. And that gives you, on a calculator or in your head, 47.5 minutes. The mid-range is 47.5 minutes. But obviously, if we have an outlier, either a low outlier or a high outlier, any kind of outlier, it's going to knock the mid-range way out of the park. It's just going to mess everything up. So it's not as useful as any of the other measures of center that we've learned about. Okay, so that actually is going to complete our first video on this section, which was section 3.1. So we've learned about 4 measures of center. And, well, I guess just one more quick thing before I complete the video. I just wanted to point out on this slide, we already talked about the mean, the median, and the mid-range. For those, you want to carry one more decimal place than is present in the original set of values. Okay, so that's for the mean, the median, and the mid-range. The only thing that's a little surprising is that for the mode, you're supposed to leave the value as is without rounding. Okay, and this is true because values of the mode are the same as some of the original data values. Okay, so maybe that makes sense because the mode could also be categories, and how are you going to round a category? You can't round vanilla or chocolate because those are not numbers that you can round. So it kind of makes sense that you shouldn't have to round the mode if it can be categorical. Okay, and then we'll cover this slide, but then the rest of these slides I'm going to do in my next video. So my part 2 of this long section. Okay, so let's just do this slide and then we'll stop this video. So critical thinking, we can always calculate measures of center from a sample of numbers, but we should always think about whether it makes sense to do that. We should also think about the sampling method used to collect the data. Okay, so that completes what we just did there. This video was 3.1 part 1. Okay, so in this video we learned about the mean, median, mode, and midrange. Okay, that's what we just did. Now in my next video on the same section, it's going to be 3.1 part 2. We're going to take a look at the rest of these slides, which are going to talk about, first of all, the critical thinking of whether these measures of center are actually useful in the real world based on what data we're gathering. And then also, the other thing we're going to learn about in the next video is we're going to learn about calculating a weighted mean. So if you've ever wondered how to calculate your grade in a course when they give you percentages for each category, we're going to learn how to do that. Or if you're wondering about your GPA a particular semester, that's also a weighted mean. Okay, so thanks for watching. See you on the next video.